Okay. So you're talking about the time scaling property. X of t is a periodic signal with time period cap t, fundamental radian frequency of omega naught, which is 2 pi divided by t. I can express a periodic signal x of t as a summation of orthogonal functions, in this case exponential functions, e to the jk omega naught t, where k is the index corresponding to each harmonic, omega naught is the fundamental radian frequency, in ak are the kth Fourier series coefficients. These could be real, these could be complex. So you multiply ak and with their corresponding orthogonal function and sum up all those projections and you get your x of t. Now the time scaling property says if alpha is greater than 0, notice we are not talking about the time flipping property here, we are focusing on the time scaling. So we are assuming that alpha is greater than 0, x of alpha t, so the time scaling factor is alpha here. It is also going to be periodic with a different time period. The time period is going to be now t divided by alpha. So t divided by alpha is now the new period of the scaled signal. And consequently, the fundamental radian frequency of the scaled signal will be omega naught prime, which is alpha times omega naught. So if we were to write the Fourier series representation of x of t using the exponential Fourier series, we can say x of alpha t, we are simply changing that. X of alpha t is going to be summation k equals negative infinity to infinity. And because the time period has changed and the fundamental radian frequency has changed, only alpha omega naught is going to change. The remaining, the Fourier series coefficients are not going to change. So what does this mean? I can find out the new Fourier series coefficients to be the same Fourier series coefficients as before. The only thing that has changed is the frequency at which those Fourier series coefficients happen, right? So I've just changed that from omega naught to alpha omega naught. That's it. So let's go ahead and answer these two questions here. The first question is, when a signal gets time scaled, maybe it gets squeezed or expanded, right? Like compressed or expanded horizontally. When a signal gets time scaled, do the Fourier series coefficients change? Did AK change? If you notice, AK here is the AK there. So the Fourier series coefficients did not change. So the answer to that is no. So let's ask the second question. When a signal gets time scaled, does the Fourier series change? Emphasis on Fourier series, the exponential Fourier series. The Fourier series has changed. So the orthogonal set of functions e to the jk omega naught t, that has changed now to e to the jk alpha omega naught t, but the coefficients did not change. So that's the difference when you time scale a signal. All right, next property. Well, let us talk about this a little bit more. Now, imagine a signal being stretched out, right? So you are actually doing this. Say, for example, if I sketch over here, say you have something like this, and so on, and you are stretching this. So essentially, you are making this like that, right? And like that, and so on. So you are stretching it out. If you stretch out the signal, what is going to happen in the plot for k versus ak? Are the coefficients going to be closer to each other, or are they going to spread out more? So coefficients, or the Fourier series coefficients with respect to k will be closer or farther apart? So Ryan says farther apart, like spread out. Here is how I think about this. I say if I if I stretch this signal out to this, I have essentially made things slower, right? If I make things slower, I will have more things that are at lower frequency. So AK, notice I'm going to just spread out this one, right? So I'm going to be accumulating that to closer to each other. So these guys are actually going to get closer and closer and closer as I stretch that signal out. So in one, you're talking about time. In the other, you are relating to a frequency at integer intervals, right? K omega naught, 1 omega naught, 2 omega naught, 3 omega naught, and so on. You guys see that? So if you make things slower, that means lower frequency. We will talk more about this particular concept later on again, but just so the answer is closer here. Things will get closer and closer in the Fourier series domain. All right, let's keep moving. The next property we are talking about is the conjugate property. So what happens when you do a complex conjugate operation in the time domain? If x of t is t periodic, meaning periodic signal with a time period of cap t, and we are given that the x of t, the time signal, has Fourier series coefficients as defined as a sub k, then a new signal y of t, which is the complex conjugate of x of t, and the Fourier series coefficients of that, let us suppose, are b sub k, then the conjugate property says b sub k will equal a sub minus k complex conjugate. So let us try to write a few things over here. So the minus sign here indicates what? It indicates flip AK about vertical axis. And over here, the x-axis is k. And if you were to sketch AK here, whatever those are, you would simply flip that, right? So if you flip that about the vertical axis, you get a sub minus k. How about the complex conjugate? That means that AK, from, if they are complex, say A, or I should say maybe x plus j, not even x. Let us use, let's say I use A1 plus A2. If I find for each k, right? If I find the conjugate, I get A1 minus A2, right? So each coefficient will get complex conjugated, and there will also be a flip about the vertical axis. So that's what the property says. Let us try to quickly prove this. AK, the Fourier series coefficients of x of t, can be found out by applying the Fourier series formula, which is 1 over t integration for over one time period. In this case, we are choosing the time period to be 0 to t, x of t e to the negative j k omega naught t dt. We have seen this many times. Now for bk, we can use the same formula, but instead of x of t, now we are going to use x conjugate of t, because the signal for which bk are the Fourier series coefficients is x conjugate or x complex conjugate. Everything else remains as is. Now, with a little rearrangement, because this is x complex conjugate and this is e to the minus jk omega naught t, I can pull out that complex conjugate operation outside of that integration, and then inside the integration I will leave x of t and e to the plus jk omega naught t. So if I conjugate that, it is the same thing as writing x conjugate and e to the minus jk omega naught t as it was earlier. And now if you notice this, this is simply the Fourier series coefficients of x of t. However, this is with the flipped k, because in the equation it is minus k, over here it's plus k, so it's that. Let me highlight this with yellow maybe. So all of this is simply a sub minus k, and then you have this on top because you have isolated that. And then that proves that the new Fourier series coefficients for y of t are related to ak as flip ak about the y-axis and then complex conjugate them. Next, an implication of this complex conjugate property is this. If x of t is real, which means that the complex conjugate of x is the same as x, then we can say ak equals a minus k conjugate. We are simply saying then the Fourier series coefficients of x of t and x conjugate of t should be the same because x of t is real. And if these guys are equal, I can write two more statements about their magnitude and phase. Now, if you look at the magnitude is distance from the origin. So if you have AK or you have AK conjugate, it should give you the same. So magnitude of AK will be the magnitude of A minus K conjugate, and you will get A minus K because the conjugate doesn't matter here. The distance of A plus JB and A minus JB from the origin is the same. What is that? It is the square root of A squared plus B squared, right? Now looking at this statement, if magnitude of AK is the same as the magnitude of A sub minus K, we can say the magnitude of AK is an even function. So all the Fourier series coefficients, if you sketch on K, AK, whatever you find here will be the same thing as whatever you find here. If you flip the signal, it will be the same. It is symmetric about the vertical axis. That's the even property. We have seen this before. Next, let's talk about what happens to the phase. The phase of this complex number AK, where K is the kth harmonic, right? So that's the index of which harmonic we are referring to. The phase of this is going to be the phase of this because of that. So this is A sub minus K conjugate. Now, what is the phase of a complex conjugate number? Well, if you see this, A minus JB, what is the phase? Over here, it is going positive. Over here, it's going negative. So whatever you have theta here, this will be minus theta. That's it. So you have the negative phase of A sub minus K. So when you do a complex conjugate, you essentially flip that about the horizontal axis. So instead of going plus theta, you're going minus theta, which means the phase or the argument of A sub K is odd, symmetric about the origin. AK minus A sub minus K, very similar to x of t equals minus x of minus t. In this case, our t is K, right? Yes. So Alan says, are these only true for x of t real? Yes, these are only true when x of t is real. So complex conjugate property, we are leveraging that to write a special case for x of t is real. let us move on to the next relevant example here. Let us say we want to find out the Fourier series coefficients of the real part of x of t. For this, we would need a reference. When you have a complex number z, which can be written as x plus jy, and obviously the complex conjugate of z is going to be x minus jy, combining these two, or essentially adding them up, what do you get? Z plus z complex conjugate is going to be 2x, which simply means it is going to be 2 times the real part of z, because x is the real part of z. We can rearrange this to write real part of z, real part of the complex number z, is going to equal z plus z conjugate divided by 2. So we will use this a few times today, but we will also use this for doing this example. So I'm going to use red here and go forward. So let's say what is real part of x of t. So real part of x of t, what is it? Based on the note, it is going to be x of t plus x complex conjugate of t divided by 2. All right. So I need the Fourier series coefficients of x of t. I need Fourier series coefficients of x complex conjugate of t, and then I can divide them by 2. Note, linearity is something that we have already proved for Fourier series coefficients. So we are going to use linearity as well. All right, let's go forward and say, all right, x of t, my Fourier series coefficients are, let's assume they are ak. And for x complex conjugate of t, my Fourier series coefficients based on the conjugate property are going to be a minus k complex conjugate. Now, add them up, divide by 2, which means the real part of x of t, the Fourier series coefficients should be a sub k plus a sub minus k conjugate divided by 2. All right, there's a question on the chat box. I will answer that in just a minute. So that's as far as the Fourier series coefficients of the real part of x of t is concerned. If you are given that the Fourier series coefficients of x of t is ak, then the real Fourier series coefficients of real part of x of t are going to be ak plus a minus k complex conjugate divided by 2. Now, if the question was about imaginary part, what would you have done? Imaginary part of x of t. What would you have done there? Well, imaginary part of x of t is simply x of t minus x conjugate of t divided by 2j. So if you know the Fourier series coefficients of x of t, then you can simply say ak minus a sub minus k complex conjugate divided by 2j, and you would get the Fourier series coefficients of imaginary part of x of t. Right? So you can say imaginary part of x of t Fourier series coefficients are a sub k minus a sub minus k complex conjugate divided by 2j. All right. The question on the chat box is there is some confusion about the complex conjugate aspect of a sub minus k. To get the complex conjugate, do you switch the sign before ja2, or do you divide the complex conjugate? Okay, so here let us tackle that over here. Let us suppose you have this. Let us suppose you have only two. One is over here and one is over here, and let's say this is k, this is at 1 and -1, this is ak, and I'm just going to I'm just going to say that this is, say, I can use x here, x plus jy, and say this is, I don't know, c plus jd, some two arbitrary points. So in order to find a sub minus k, what would you need to do? Well, a sub minus k, this remains as k. I'm trying to find a sub minus k. This would flip, right? So this will be c plus jd, and this guy will be x plus jy at 1 and -1. So that's flip about the y-axis to get a minus k. Then, if you want to add a conjugate, let us add that in blue. What do? You simply make this guy minus and this guy minus, and done. So I hope that was helpful to go from a k to a sub minus k conjugate. All right. That's it. Yeah, that's it. Let's move on to the next property. Property number 8, multiplication property. Now, multiplication property happens to be one of the most useful properties that you will find at many places in the next coming 2-3 weeks. Remember what I said about when we were talking the last time on Monday. I said if you do something in time domain, there will be a corresponding operation in the Fourier series domain for the Fourier series of those signals. We will see that multiplication in time domain results in discrete convolution of the Fourier series coefficients. We are going to prove this, but this relationship of time and frequency and multiplication and convolution is something that I want you guys to get right away. This is going to help is going to help you a lot. Multiplication in the time domain corresponds to a convolution in the frequency domain. In this case, we are talking about the Fourier series, those specific frequencies. But when we go on to talk about Fourier transform and think about frequency domain, you will see this same aspect play out again, where multiplication in one domain corresponds to convolution in the other domain. And it works backwards too. Multiplication in frequency domain will be a convolution in time domain. So this kind of back and forth, equivalent, so corresponding operations, those are the tricks. Those are the tricks that will help you with Fourier series, Fourier transform, Laplace transform, and so on. So this time around, the convolution is not going to be the dreaded do a graphical convolution to find these things. The convolutions over here are supposed to be, all right, can I use a property of an impulse? Can I use a property of convolving two rectangles? The focus is not going to be on the convolution. The focus is going to be on the property, right? The multiplication and convolution being related are essentially a Fourier transform pair. So it's not convolution all over again. It is just the use of convolution all over again, right? So it's not as bad as it seems right now, is what I'm going to say. Plus, it is discrete convolution right now, so we have array algorithm too, right? All right, let's see. So there are two signals that we are going to try to multiply. There is a x of t, there is a y of t. Both are having the same time period t. and we are multiplying them in the time domain. So z of t, our new signal, z of t, is defined as the product of x of t and y of t. X of t, the Fourier series coefficients are a sub k. Y of t, the Fourier series coefficients are given as b sub k. And the multiplication property says that if you multiply the two signals of the same time period cap t in the time domain, then the resulting Fourier series coefficients of z of t, which is defined as c sub k, is going to be the discrete convolution between a sub k and b sub k. Now notice I said discrete convolution because a sub k are discrete elements, b sub k are discrete elements because k is discrete. When k is 1, we are talking about what is the Fourier series coefficients for the frequency 1 omega naught and minus 1 omega naught. And when k is 2, we are talking about the second harmonic. When the k is 3, we are talking about the third harmonic and so on. So those are discrete. Does ck correspond to x of s? Well, x of s, z of s. So let's see this. I can say c sub k are the Fourier series coefficients of z of t. Yes. But are you talking about the frequency domain? Oh, no. So you're talking about the Laplace variable s, right? So in that case, s is a continuous frequency. So you would have to do a continuous convolution between the Fourier transform, or in this case Laplace, right? So the Laplace transform of x of t and the Laplace transform of y of t, then it is okay. So everything would have to go to frequency domain. Right now we are talking about the Fourier series coefficients. So we are not there yet, but you're on the right track. It is going to be the same over there as well. So let's suppose if you want to really talk about that, let's just do it. I can say Laplace is going to be what? X of s, y of t, Laplace y of s, then x of t multiplied by y of t, Laplace transform is going to be x of s convolution y of s. But in this case, it is going to be a continuous convolution because s is a continuous Laplace variable. So there is a similar property for for Laplace, but we are jumping like ahead, like 2-3 weeks ahead now. So let's not jump there yet. All right, so I hope that that clarified some things. Let's come back to this. Let me erase this, let me erase this, and let me erase this, and then have this as a separate conversation. All right, so the claim is that if you multiply the two signals for which you have the Fourier series coefficients. Oh, by the way, when you talk about Laplace, there is no condition that x of t and y of t has to be periodic. Over here, x of t and y of t are periodic, right? So this is general, very, very generic signals under consideration for Laplace. All right, so let's come back to this. X of t Fourier series ak, bk, and then you do a discrete convolution between ak and bk to find the Fourier series coefficients of the product of x of t and y of t. All right, so let's do this first. Let's do a proof first, and then let's do an example, which is actually very, very helpful. So let's start with z of t right at the top. Z of t is x of t multiplied by y of t. X of t can be written as summation of its Fourier series coefficients a sub k multiplied by the exponential Fourier series e to the j k omega naught t. On the other hand, y of t can be written as another summation. The Fourier series coefficients are b sub k. In this case, we have changed the variable to L because we have already used k for the previous one. So in this case, our b sub L are going from in negative infinity to infinity. We take those coefficients b sub L for each corresponding exponential function e to the j L omega naught t. Notice over here, we are using the same omega naught, right? Same omega naught in both. So it's the same time period for both. Next, if you have multiplication over here, one is with respect to k, the other is with respect to L, you can combine these summations into one. You can say double summation, one is with respect to k, the other is with respect to L. And inside those summations, you have a sub k, b sub L, and because you have the exponential, complex exponentials here, you can combine them to write e to the j k plus L times omega naught t. Next, I want to get rid of this. I want to get rid of this k plus L. I want that to be one entity. So what I'll do is, I will do a simple change of variable here. So I will say m equals k plus L, which implies that k will equal m minus L. So what I'm going to do is I'm going to apply a change of variable to this function so that I can write it in a different way, a slightly modified way. So notice over here, I have the summation that is with respect to L goes as is. With respect to L, I have all the things that have an L in them. What are those? A sub m minus L, because for AK, I have substituted a sub m minus L. BL, that's it. Those are the only ones that have a L inside them. What remains is e to the j times m omega naught t, where m also depends on L. But these are the ones that are directly have an L in them. Now notice what this is. This is essentially a convolution between A and B. How do I know that? Well, I know that because I can refer to y of n. What is y of n? Discrete convolution. We said m equals minus infinity to infinity x of n h of n minus m. Actually, this should be m. Now, there is a one-to-one mapping between what you see over here and what you see over here. M. Oh, by the way, convolution is commutative. So you write n minus m here or m there, it shouldn't matter. So x of m is like b sub L. M going from negative infinity to infinity, L is going from negative infinity to infinity. Here you have a sub m minus L, you have h of n minus m. So this is exactly, so what do you get? X, y of n, right? So you get what? C sub m, right? So that's how you can map these two. That's exactly a discrete convolution exercise, the one that you see in the red box. So you can write that red box as Cm now. Let's see, Cm right here. And then e to the j m omega naught t remains as is. And then the summation from m equals negative infinity to infinity remains as is. Notice what this is. Let us use a different color here, maybe brown. So what is this? Sure. What's that? That is essentially another periodic signal. with time period cap t. So omega naught, which means omega naught is 2 pi divided by t. The Fourier series coefficients of this new periodic signal is C sub m. And we have been calling that another periodic signal what? Z of t. Right. So that's the Z of t that we have been talking about. All right. Now we just write the summarizing statement. C sub m was this, the red box. Summation L equals negative infinity to infinity, A sub m minus L, B sub L. Convolution is commutative, so you can rewrite this as A sub L, B sub m minus L. And because this is discrete convolution, you can just indicate that by using the convolution operator, A sub k asterisk b sub k. Those are your Fourier series coefficients of z of t. So that's how you can quickly prove the multiplication property. Some textbooks call this time multiplication property because it is specifically talking about what happens to the Fourier series coefficients when you do multiplication in the time domain. All right, so that's your time multiplication property. Let us apply that time multiplication property to find the Fourier series coefficients of the product of these two signals. Let us define them first. One is a pulse train. Let's use right here. Let us say this is x of t, and I say that the Fourier series coefficients of x of t are a sub k. And let us see the cosine t, which is also a periodic signal, y of t, whose Fourier series coefficients are, let us suppose, b sub k. So our first goal will be to find a sub k and b sub k. Sketch it out quickly. Let's see. Boom and boom. And I can also do this. And let's see, for come on. And let's see, for the next one, it is going to be cosine, and the time period is pi. So I don't know. It's kind of okay, but I think you guys get the idea. All right, let's mark things out. First, we have the pulse train. There are two time periods, right? Pi over 2 and 2 pi. 2 pi refers to the time period of the periodic signal. So if this is 0, then this guy will be what? 2 pi. And this guy will be negative 2 pi. And the pi over 2, which we have been calling t sub 1 in the previous references, is pi over 2. So that's pi over 2 there and minus pi over 2 there. And the height, of course, is 1. So this is our x of t, the first signal. Next, y of t. Cosine, that should be simple. 1 there, negative 1 there, that is 0, that is pi. This should be plus pi over 2, this should be minus pi over 2. And it's periodic with 2 pi, so when it happens again, that should be 2 pi. Is that right? Yes. Pi over 2. Oh, pi is over here. All right. So when you multiply these guys, you're essentially saying that between negative pi over 2 and pi over 2, it is going to look like a cosine. So it's a half sinusoid. And for all the other times, so between pi over 2 and 3 pi over 2, it is going to be 0, and it is periodic. So Clara, the Fourier series coefficients are not directly in the frequency domain, but they are related to the frequency domain. So when you think about, all right, let's talk about this, K and AK, right? So what is K? K corresponds to the index. Index of what? Well, index of 1 omega naught, plus and minus 1 omega naught, plus and minus 2 omega naught, plus and minus 3 omega naught, and so on, right? So we are talking about what is the coefficient, what is the projection of the signal on on the orthogonal set, which is comprising of complex exponentials at frequency 1 omega naught, 2 omega naught, 3 omega naught, and so on. So when you know AK, it will have a magnitude and phase, but it will give you the coefficient that corresponds to the frequency 1 omega naught, 2 omega naught, 3 omega naught, and so on. So you can think of that as the discretized frequency domain. So it's not directly frequency domain because we reserve that term where the signal is continuous in frequency domain. Like that's what we have to use Fourier transform for. But right now, because the signal is periodic, it's going to be a sampled version of its Fourier transform. So we are jumping ahead here, but it is related to the frequency domain, but not directly frequency domain. All right, let's come back. So we need to multiply these two signals, and in order to do this, in order to find the convolution here, we need to find AK and BK, and then we can convolve them to find the convolution, the Fourier series coefficients of the signal. Let's call this Z of t. So what is AK? We know this from previous result. It is 2t1 divided by t sinc k omega naught t1. That was for all k. This is simply using the reference result of the pulse train. In our case, t1 is pi over 2, cap t is 2 pi. So you substitute that, what do you get? 2 pi over 2 sinc k remains as is. Omega naught, okay, we need to find omega naught. What is omega naught? If time period, let's do it in blue, time period is 2 pi, then omega naught will be 2 pi divided by 2 pi, so it should be 1. So let's just leave that as a reference there, and then come back. Times 1 times what? T1. T1 is pi over 2. Done. That is for all k. Divided by 2 pi. Simplify, what do you get? Half sinc k pi over 2. Note, AK can also be written as 1 over pi k sine k omega naught t1 for all k. All we are doing is using the definition of sinc. Using sinc x equals sine x over x. So you can write this in two different forms. But we are going to use this for now. Okay, so we found AK. We are left with BK. BK, let's do it on a separate slide, but I'm going to copy this for now. Copy and add. So what is y of t? Y of t is simply cosine t, and this is t. So my goal next is to find the Fourier series coefficients of a cosine function. All right, let's do that. So what is cosine t? Let's do it for cosine omega naught t, general case. I can say, cosine omega naught t equals e to the jx, j omega naught t, plus e to the minus j omega naught t divided by 2. Euler's identity. I can write cosine using complex exponentials. We know this from before. I also know that I can write any periodic signal like a cosine using its Fourier series coefficients. So if I'm using exponential Fourier series coefficients, I can write this as negative infinity to infinity b sub k e to the j k omega naught t, right? Now, all I have to do is compare the coefficients over here with here. What do I get? Compare coefficients of e to the j k omega naught t. And if you observe carefully, you will see that you will only have two non-zero Fourier series coefficients. One of them is b sub 1, which will evaluate to half, and b sub minus 1, which will evaluate to half. Because as you can see here, the only time where you get e to the j omega naught t is when k is 1. Over here, k is minus 1. And when k is 1, you have an amplitude of half. And when k is minus 1, you have an amplitude of half. And all the other coefficients are 0. So you have b1 as half and b sub minus 1 also as half. In other words, I can write b sub k, the Fourier series coefficients of cosine, as half an impulse at plus 1 and an impulse at minus 1. I think I said it reverse. This is at plus 1 and this is at minus 1. So let's also sketch it out just for the sake of completeness. This is k, this is b sub k. Those are the coefficients of the cosine function. You only have two of them. One is here and one is here. One, negative 1, 0, half. Done. And it kind of makes sense, right? When you say, what frequencies does this have? Cosine omega naught t. You will say the frequency is, the radian frequency is omega naught. That's it, 1 omega naught. So you should have only 1 and minus 1 for k. Alright, so we have found AK and we have also found BK. Let's box this up as well because we are going to need these two when we convolve. So we have found BK here. We had AK from earlier. Let us try to combine them. So we said Z of t equals X of t multiplied by Y of t, and the Fourier series coefficients are C sub k which equals a sub k convolution b sub k, that's from the multiplication property. So c sub k I can write as half sinc k pi over 2 discrete convolution half impulse k plus 1 plus k minus 1. Now when you use, so here is where you can leverage the property convolution with an impulse. Well, let's do the first one first. So let's do this guy with this guy. What do you get? You get half and half, 1/4. Sinc. It's the same function but shifted to wherever the impulse is. K plus 1 pi over 2. So that I should shade in yellow. Next, maybe I'll use a different color here for this guy. What do I get? I get 1/4 again, sinc again, k minus 1 in this case, pi over 2. Done. So again, we use linearity, right? We use linearity to convolve these two guys to find the Fourier series coefficients of z of t. How does z of t look like? When you multiply those two signals, it literally looks like this, right? This is time, this is z of t, which is x of t multiplied by y of t. This kind of looks like this, right? And it keeps going. So this is 1, this is 0, this is pi over 2, this is negative pi over 2, this is 2 pi, negative 2 pi. You use the sampling property to get k plus 1 and k minus 1. So for k plus 1 and k minus 1, do you mean how did I go from here to here? So the way I went from here to here, you see this can be written as an impulse at plus 1 with an amplitude of half. So that can be written as half delta of k minus 1. And this guy can be written as half delta of k plus 1. So I just added those up for that. Oh, for the k terms in the sinc. Okay, so here I used the property convolution with impulse. Let me write that down here. Convolution with impulse. X of t convolved with delta of t. Sorry, I'm writing it for continuous time. T minus t0 is x of t minus t0. That's what I used. So if you want to think of it in terms of discrete, I can write it like this. Copy, paste, maybe paste it here, zoom in, erase, t becomes n, this becomes something else, this becomes something else, bracket, okay. Let's see. X of n, delta of n minus n0, x of n minus n0. That's what I used. All right. Questions about these guys? This example. So in this example, we see a lot of things at play, right? Like you see, you review the Fourier series of pulse train. You find the Fourier series of a cosine. you find you apply the multiplication property. On the same note, let us try to find the Fourier series coefficients of this. Let us see if we can do this. Sine omega naught t. What are the Fourier series coefficients of that? So sine can be written as e to the jx minus e to the minus jx divided by 2j. So what should be the Fourier series coefficients here? Well, if you again write this as a summation and then compare coefficients just as we did earlier, you should be able to say that let's say a Fourier series coefficients over here should be what? 1 over 2j at k, this is plus 1, so this is minus 1 there, k is 1 and then k is minus 1, minus 1 over 2j delta of k plus 1. You guys see that? So essentially a sub 1 is going to equal 1 over 2j, a sub minus 1 is going to equal negative 1 over 2j. Okay, let's keep moving. The next theorem, Parcells Theorem. So this is going to be about relating the power of a periodic signal x of t and looking at its power by summing up the power in all the harmonics. And before we get started with the proof of Parcells theorem, I want to say this. Does the power of any signal change no matter which domain you look at it from? So Ryan brings up an interesting point. Omega naught doesn't matter. No, it doesn't matter. You see this? Omega naught is whatever radiant frequency of that sine is. So when you say A1 and A negative 1, you are literally saying at plus and minus 1 omega naught, right? So it applies for all our Fourier series. So when k is 1 or negative 1, we are talking about what is the Fourier series coefficient of the complex exponential at plus and minus 1 omega naught. And then you will have, all the others, plus and minus 2 omega naught, 3 omega naught, 4 omega naught go to 0. So that means that none of those frequencies are present in sine omega naught. Right? You guys see that? So omega naught is the radiant frequency of the periodic signal. The Fourier series coefficients are not related to the frequency. The Fourier series coefficients correspond to the shape of that periodic signal. Okay, so in other words, what happens when I change the frequency here of sine omega naught? If I go up and down in frequency, does this change? K, AK? No, it doesn't change. Even if you increase the frequency here or decrease the frequency here, this will continue to be A1 and A minus 1. 1 plus 1 divided by 2j and minus 1 divided by 2j. It kind of goes back to the same property that we had at the very beginning, the time scaling property. When you stretched the signal or squeezed the signal, the Fourier series did not change. Fourier series coefficients did not change, only the Fourier series changed. All right, so let's see. Let's go back to where we were. Okay, so Parcells theorem. So my question was, does it matter if I look at the signal in time domain? Does it matter if I look at the signal in using its Fourier series? It should not matter. Power in all domains should be the same, no matter which angle you look at it from, which perspective you look at it from. So that's kind of what Parcells theorem is about. So let's try to look at it. Suppose x of t is a periodic signal with time period t. X of t can be written as a summation of all the Fourier series coefficients multiplied by their respective exponential Fourier series. X conjugate of t can be written as summation over all k, a sub minus k complex conjugate with e to the j k omega naught t. We have seen this before. This is using the conjugate property. Multiply these two signals. What do you have? You have a new signal whose Fourier series coefficients are b sub k, and it is going to be a periodic signal, so I can express that as k equals negative infinity to infinity, b sub k e to the j k omega naught t. And I know from multiplication property that bk should equal the discrete convolution of ak and a minus k complex conjugate, because I'm multiplying them together here. Next, I can write bk using the definition of discrete convolution. Summation L equals negative infinity to infinity, a sub L and multiplied with a sub minus k minus L conjugate. So this is just using the discrete convolution of, there's additional variable, right? It's related to this, x of m, h of n minus m. It's related to that. A sub minus k minus L, complex conjugate remains as is. Bring in the minus sign inside the parentheses, you have al minus k complex conjugate. All right, so we are going to need this result, and we'll copy and paste it on the next slide at the top. So this is the statement from before. Now substitute k equals 0 in this. What do you get? B sub k becomes B sub 0. What does this become? It becomes that, because k is 0. But B sub 0, we know, should be the DC value of the product of those two signals. We know that because k equals 0 corresponds to the DC value, and B is corresponding to the Fourier series coefficients of the product of x of t and x complex conjugate of t. So by using those two statements, I can say B sub 0 should be 1 over t integrate over one time period x of t multiplied by x complex conjugate of t. And by substituting 0 there, it comes down to that. Now once you have this, we are also going to need two more results. One is a complex number z multiplied by the complex conjugate of the same complex number z is magnitude squared of z, where z is the magnitude of z. Now if you apply this over here on the left hand side, what do you have? On the left hand side, you have 1 over t remains as is, integration 0 to t remains as is, and then inside you have x multiplied by x conjugate, so that becomes the magnitude squared of x. On the right side, you have summation, which remains as is, and then al multiplied by al conjugate becomes the magnitude squared of all those coefficients. Let's just use this. Now if you observe, so that's Parcells theorem, and if you look at it on the left side you have variable t, on the right side you have variable L. T corresponds to time, which means the left entity is the power in the time domain signal x of t. On the right, you have L, which corresponds to the index of each harmonic in x of t, which means this is going to be the sum of powers in all the harmonics that make up x of t. So Parcells theorem says that those two power entities are the same. Next, we are going to move away slightly from exponential Fourier series and talk about trigonometric Fourier series. And the reason we can do this is simple. If our orthogonal set can comprise of complex exponentials, those complex exponentials can be translated into cosines and sines. So I should be able to use trigonometric Fourier series as well to represent an orthogonal set. But I'm going to have to spend some time trying to figure out a sub 0, the DC value, b sub k, the coefficients that correspond to the cosine part, and c sub k, the coefficients that correspond to the sine part of the periodic signal x of t. So earlier we were simply finding out a sub k, and we were saying a sub k are the exponential Fourier series, and we were splitting it up into two parts, right? We said a sub 0 and then we said a sub k where k is not equal to 0. But now when we talk about trigonometric Fourier series, we try to find out three things. One is the DC value, which is the cap a sub 0. The other one is bk, and the other one is ck. So let's go through this. A sub 0, b sub k, and c sub k are the trigonometric Fourier series coefficients. Now let's start with our definition. The definition of periodic signal being able to be represented as a weighted sum of a set of orthogonal functions. In this case, our orthogonal functions are the the complex exponentials. So we are trying to go from here to there. Let's see the connection. Now assume that x of t is real. If x of t is real, based on the conjugate symmetry property that we saw earlier, ak complex conjugate will be the same as a sub minus k. This is a property that we can prove, and it's laid out in the tables. This essentially says that if the signal that you're considering is real, the complex conjugate of its Fourier series coefficients will be the same as the ones that you flip, which essentially means this. If I go all the way back, I think, right? So if you look at this, if this was real, then you do the conjugate or you don't do the conjugate, it will be x and c, right? So it will be the same. All right. So by using this conjugate symmetry, we can write x of t as a summation over all k, ak e to the jk omega naught t, which is the one from here. We can split up this summation into three pieces. And there is a reason why we are splitting it up into three pieces, because we want to go to a cosine, sine, and some DC value. The first piece is a summation over all k, where k is between negative infinity and negative 1, and then a sub 0, and then another summation where k is going from 1 to infinity. We'll do a simple change of variable here, m as minus k. So when we do m as minus k, our summation doesn't change, ak doesn't change, e to the jk omega naught t doesn't change. On the left side, we applied a change of variable, m equals negative k. The limits on the summation became m equals infinity to 1, a sub minus m, and e to the minus jm omega naught t. Let us change it back to k. M equals k. What do you have? K equals 1 to infinity. So you sum it this way or sum it that way, it should be fine. 1 to infinity a sub minus k, e to the minus j k omega naught t. So we change the variable twice here to get it into this form. Next, we are going to go back to our original, go back to those three pieces. One is what we reduced. So let's see, let's back up a little bit. So this over here, 1 to infinity, is what we are using here. Then from before we had a sub 0, that remains as is. And then we had another piece from 1 to infinity. That's going to be the piece here. Now that we have done this simple trick, and the trick was to simply get it from negative infinity to negative 1 to 1 to infinity, so that we can combine these two guys. Or we can write it in a different way, which later on we can combine. So if you see this, if x of t is real, a sub minus k can be written as ak conjugate. E to the negative jk omega naught t can be written as e to the jk omega naught t complex conjugate. A sub 0 remains as is, and this summation remains as is. Next, multiplying the complex conjugates, I can pull out that complex conjugate after the multiplication. So you have k equals 1 to infinity, ak multiplied by e to the jk omega naught t, the entire thing getting complex conjugated. A sub, the rest two terms remain as is. We are going to use the property of complex numbers here next, which we already noted to z plus z complex conjugate. What is z plus z complex conjugate? It is simply 2 times the real part of z. We did that earlier note. So you have a complex conjugate entity here. We have the complex number here. So the sum of these two should simply be 2 times the real part of that. A sub 0 remains as is. So a sub 0, we have been using blue for that. Blue, blue, and blue remains as is. And we have simply combined the other two. So let me show you in green here. This has been combined using the note with this to get that. That tells you that I can represent x of t in this form if I know the Fourier series coefficients of x of t. Then I can plug those Fourier series coefficients over here, and then the remaining things are given, and I can express x of t like this. Now, for trigonometric Fourier series, we can write a few special cases. The first special case is when a sub k, the Fourier series coefficients of x of t are real. If ak are real, what happens to the real part of ak e to the jk omega naught t? Well, e to the jk omega naught t can be written as cosine k omega naught t plus sine k omega naught t plus j sine k omega naught t. So it should simply be ak cosine k omega naught t. Right? So if I say what is the, let's focus on this real part of ak e to the jk omega naught t. Real part of ak e to the jk omega naught t. So if ak are real, what is going to happen? This can be written as cosine plus j sine. Because I am using the real part of ak is ak because ak is real, and real part of this guy is going to be cosine because sine will cancel out, so you get cosine from there. So that's special case number 1. If ak is real, x of t can be written as a sub 0 summation k equals 1 to infinity 2 times a sub k cosine k omega naught t. Now the second case, ak is complex, but we are writing that complex ak in a polar form. Meaning I am writing ak as some magnitude, some phase. Magnitude is the absolute value of a sub k, and the phase is the argument of a sub k. And we know from complex numbers that I can find the magnitude of ak by finding the real part of ak squared plus imaginary part of ak squared. And the argument can be found as the inverse tangent of imaginary part of ak divided by the real part of ak. So if you plug these in here, what do you have? For original x of t, I have a sub 0 plus 2 times k equals 1 to infinity 2 times real part of ak e to the j k omega naught t. That's that right there. 2 remains as is. The magnitude of ak comes out because it is real now. And then you still have to find the real part of e to the j k omega naught t, which is from this guy is from here. And let's see, this guy is from here. Because you are trying to find the real value, you multiply those two complex exponentials, you simply get a cosine with the argument k omega naught t plus the argument of a sub k. That will be the real value, and everything else remains as is. So all these guys remains as all these remain as is, and you simply find the real value of that by using Euler's again to write that as cosine k omega naught t plus argument of ak. That's your second case. This is when you are representing the Fourier series coefficients in the polar form. Another convenient way to do this is to write the Fourier series coefficients in the Cartesian form or rectangular form. A plus jb, or real part plus j times imaginary part. So if that is the case and you apply the same sort of steps, you will get x of t, which can be represented as this. Now the question is, all right, these are the three special cases, but we were after finding the trigonometric Fourier series. So where is the connection? Well, the connection is here. If you see this, you have three entities. One is the DC value, the other one is the coefficients of the cosine, then there is the coefficients of the sine. So you will simply have to compare coefficients of x of t here with, in this form, to find a0, bk, ck. Those will be your trigonometric Fourier series. In other words, trigonometric Fourier series coefficients are related to the exponential Fourier series coefficients, and we have done that for three special cases. So by comparing coefficients, you can find out the capital A sub 0, capital B sub k, and capital C sub k. All right. So that's as far as trigonometric series, Fourier series is concerned. Now, if you guys bear with me for a few more minutes, I'm going to wrap up this conversation about response of LTI systems to cosine inputs, because I really want to start talking about Fourier transform in the next lecture. So let us say I want to find out the response of LTI systems to a sinusoidal input. And the sinusoidal input that I'm considering over here is cosine omega naught t. So if that was given to you, how would you find the output y of t? Well, this is a LTI system. I know the impulse response h of t. I know the input cosine omega naught t. So some might say, fine, let's just simply do the let's do the continuous convolution here. So let's do a cosine omega naught t convolved with h of t, and you're done. And you would be right. You can do this convolution. But I'm going to try to express cosine omega naught t using Euler's. So I should be able to do that as well. So if I was trying to find the output, the response of LTI system when the input is a sinusoid, and I know that I can express a sinusoid using its Fourier, using complex exponentials. So let's try to find the output to go from here to here. Let's try to find out the response of LTI system to a function like this, e to the st, where s is sigma plus j omega. It's your Laplace variable. We looked at this a little bit. Earlier when we said, yeah, a complex exponential is very useful. Why? Because whatever goes in comes out, but there is a scaling. So if e to the st goes in, e to the st comes out, but there is an eigenvalue associated with it, which is the eigenvalue here will be, what will be the output here? It will be, let me not write y of t. Let me just write the output in time domain. E to the st, that is the eigenfunction, multiplied by capital H of s. What is capital H of s? That is the Laplace transform of h of t. It is the eigenvalue of the eigenfunction e to the st. Okay, so let's do some special cases here. If the input is e to the j omega naught t, what is the output? Well, all I would have to do is find what would be the eigenfunction? E to the j omega naught t. Whatever goes in comes out, but there is a scaling. What is the scaling? Evaluate the Laplace transform at j omega naught. Done. Next, what would be e to the minus j omega naught t? Well, similar case. E to the minus j omega naught t multiplied by h of minus j omega naught. Wonderful. All I'm doing is I'm using this. E to the st goes in, e to the st h of s comes out. Eigenfunction, eigen value. That's it. And I'm substituting s as j omega naught here and s as minus j omega naught here. That's it. Using linearity, I know that LTI systems are linear. So if the input now is a sum of these two divided by 2, which is cosine, what would be the output? The output, y of t, should equal the sum of these two outputs divided by 2. So it should be e to the j omega naught t multiplied by h of j omega naught plus e to the minus j omega naught t h of minus j omega naught divided by 2. So it's the sum of, let's use blue here for this, and then you have green, say, for this, you have this, and then the 2 remains as is because there's a 2 there. Couldn't the output of e to the st also be written as e to the st convolution? Yeah, you can. It can be. Yes. So it is e to the st convolution with h of t, but that equals this. So I'm trying to write it in simpler terms. All right. So I have my response y of t as this for now. So what I'm going to do is I'm going to do a little bit of a manipulation here. So I've copied y of t from before. This is the response of an LTI system to a cosine omega naught t input with an impulse response of h of t, and h of t and h of s are Laplace transform pairs. But if h of t is real, h of minus j omega naught is the same as h complex conjugate of j omega naught. This is sort of the same conjugate symmetry that was present in the Fourier series, also is present in the Laplace domain. By using this h of t is real, the conjugate symmetry, I can rewrite my output in this form. Half remains as is, e to the j omega naught t remains as is, h of j omega naught remains as is, plus, instead of writing the second term here like that, I'm writing that as a complex conjugate of the previous one. So I'm writing that as a complex conjugate of e to the j omega naught t h of j omega naught. So if you treat the left as c, some complex number c, and the right one as c complex conjugate, notice what happens when you add c plus c complex conjugate. So when you add c plus c complex conjugate, and if you treat them in polar form, r e to the j theta, complex conjugate will be r e to the minus j theta. When you add them up, what do you get? 2r cosine theta. Which means y of t, the 2 gets cancelled. Y of t can now be written as r. What is r in this case? R will simply be the magnitude of the complex number c. What is the magnitude of the complex number c? It is simply the magnitude of this guy. Okay, so that's written up right here. What is remaining? Cosine theta. Okay, what is cosine theta? Theta should be the angle, the phase of c. What is the phase of c? The phase of c is omega naught t plus the angle of h of j omega naught, because h of j omega naught will have a magnitude and phase. So the magnitude went there, the phase gets combined with that to get this. So the output y of t can be written in this way. H of magnitude of h of j omega naught cosine omega naught t plus phase of h of j omega naught. This is a very interesting result. That result will help us answer something like this. And believe me, this is the last thing that we'll do today. Suppose I have, so all of this was done to answer this question. If the input is some amplitude, a cosine omega naught t plus phi, some frequency, some phase, and it goes into an LTI system with impulse response y of t, what is the output? By using the property that we just derived, I can say y of t equals a remains as is, because that's an amplitude scaling and linear systems don't change the amplitude. There is a first piece is what? Magnitude of h of j omega naught. All right. Magnitude of h of j omega naught. What's next? Cosine. What is cosine? Omega naught t plus angle of h of j omega naught. Okay. So cosine will have omega naught t plus phi from the input plus angle of h of j omega naught. Done. That will be your output. So you can take this and apply it to sines, cosines, any sinusoid function with an arbitrary amplitude, frequency, and phase. You know the output of that system, or you know output to that particular input. All you would have to know is h of t and its Laplace transform cap h of s. And now if you look at this, a is a contribution from the input. Phi is a contribution from the input. Omega naught t is also a contribution from the input. But if you look at the other pieces, let us use blue for this. The term here and the term here, the change in the amplitude and the phase, those two are actually the contribution from the system. for which the impulse response is h of t. So those are literally h of s evaluate h of s at frequency omega naught, which is essentially what? Cosine input frequency. So all you would have to do is find how that system responds to only that particular frequency to change its amplitude and phase, and that's it. So again, this is a very, very useful property, the response of LTI systems to cosine inputs. So if I hurried at the end, please watch the video and please ask me questions. All right, let me stop here.